Okay. I hope all of you in healthy condition today. Yeah. So this week is week 7. So this will be the last week before we have the midterm exam next week. And about the midterm exam, we will have yeah, we try to have the same uh, exam for all of the parallel class. Yeah. And because of that, we will arrange the time for the midterm exam because it looks like next week on 20th of October, it will be a public holiday. Yeah. Since the Maulid Nabi Day is postponed. Yeah. The holiday for Maulid Nabi is postponed to Wednesday. So that means it will be on public holiday. But we were still discussing with the other lecturers, with the other class, whether when is the time, yeah, for the midterm exam, whether it will be still on Wednesday, yeah, or whether we will postpone it to Saturday or other time, yeah. So we're still discussing on that. So about the exact schedule for the midterm exam, I will let you know again, yeah, through the WhatsApp group, yeah, through the WhatsApp group. Okay. Okay, so we will continue our discussion on the set of linear algebra equations. In which last week we have discussed about LU decomposition. Yeah. So did we finish the discussion about the matrix inversion using LU decomposition? Did we?
Yes, ma'am, we did.
Okay, we did. So we finished LU decomposition, yeah? So I'll do a brief review of LU decomposition in which the LU decomposition will be will be more beneficial if we have different right hand side, and this can be applied in the problem of matrix inversion, so that if we want to find the inverse of the matrix, so that will act as the unknown matrix, and so that we can use the right hand side here. The vector of the right hand side will be the columns of the identity matrix. So if we choose the right hand side is the column of the identity matrix, so that means we will have the vector here will be the result of the corresponding column of the inverse of the matrix A. Yeah. So we have learned of that last week, so that we can apply the substitutions directly without doing many times, without repeating many times of decomposition to L and U. So once we have the matrix A decomposed into L and U, so that we can use it repeatedly, because this will be stored in the memory. So that what we can do next is only repeating the substitution process. So we have the forward substitution and backward substitution, so that we can have the columns of the inverse of the matrix A. Yeah, so this is what we have learned last week. And we also have discussed about a different several variation of the LU decomposition, in which we can have Doolittle, Kraut, and Kolesky. Yeah, so this a further improvement, but we will not discuss that on detail. Yeah, so we will limit only in LU decomposition. Okay, so that we now continue. I think we've studied vector and norms as well, yeah? Okay, so that now we will continue to chapter 11, which is about special matrices and cosidal. Yeah, so special matrices here is for this method, which is chapter 11, is discussing about the solution for special matrices, in which what is a special matrices is that when we have a banded matrix. Yeah. Did we discuss this already?
Not yet.
Not yet. Okay. All right. So that when we have a special matrices, for example, we have the terms of banded matrix. So what is the term of a banded matrix? So a banded matrix is a square matrix that has all elements equal to 0, except the band centered on the main diagonal. So this means that the element, yeah, will fill only the diagonal part, yeah, not only the main diagonal, but it can be of several bandits near the diagonal. And these matrices typically occur in the solution of differential equations. So if we have a problem in engineering, and that from that problem we get the differential equations, so that we can further discretize the differential equations so that it becomes the linear equations, so that the resulting linear equation will be a banded matrix. So further about this, we will learn after the midterm exam, yeah, about the partial differential equation solution. So that in general, we can make the dimension of the banded system with the bandwidth, BW, bandwidth, and half bandwidth. So this is the how the banded matrix looks like. Yeah, so we have the diagonal element here. Yeah, and we have several elements that fills a banded area here. So here we have half bandwidth. So all of that will be the bandwidth. So the diagonal will be, the diagonal element is here. So that here we have half bandwidth plus 1. So that the bandwidth itself will be 2 times half bandwidth plus the diagonal element. So this will, this is the banded matrix, and this will arise in the partial differential equation problem. Yeah. What are the elements outside the banded matrix? So that will be 0. So all of the element here will be 0. So that the most simple example is, for example, we have 3 bandwidth of 3. Yeah, so if we have a bandwidth of 3, it means that the elements only fill 3 near the diagonal here. Yeah, 3 diagonals like this one. So here we have the term of 3 diagonal system. Yeah, it means that we only have 3 elements that fills in the coefficient matrix. And you will see this sort of case occur in the solution for partial differential equation. So if you have learned about heat transfer, so I think you take heat transfer course this semester, you might learn that if you have a problem of one-dimensional heat conduction, yeah, on a rod, for example, you end up with this sort of system. Yeah, you have if you want to find the distribution on a rod of one-dimensional heat conduction case, you will have this sort of system to be solved. So if we have a 3 diagonal system like this one, so we have an efficient LU decomposition method. So this is basically LU decomposition method as well, but it's said to be, the name is Thomas algorithm. So this is specifically for 3 diagonal system. So the algorithm consists of 3 steps. The first step is decomposition, and then we have forward and backward substitution. So very similar to LU decomposition. But because the element is sparse and it's only filling 3 bandwidth like this one, so that we can write down the Thomas algorithm as this one. Yeah. So this is the decomposition process, in which here, E here is with, we are filling with the lower matrix, yeah, and have F here is filling the element in the upper matrix. Yeah, so this is the decomposition process. So E here is filling in the lower matrix, and F here is filling in the upper matrix. So once we have the looping here, so that when we finish filling in the value, yeah, for the lower and upper matrix, so that we can perform forward substitutions, yeah, with forward substitution with the lower matrix, and then we can do backward substitution with the upper matrix here. Yeah. Okay. So this is very similar to LU decomposition, and this can be applied only for three diagonal system. Yeah, three diagonal system. It means it has only three bandwidth. And Galaxy decomposition is also a variation of LU decomposition, in which this only applies when we have symmetric matrix. So that say we have the symmetric matrix such that A21 will be equals to A12 and A31 will be equals to A13 A13. So that means that we can decompose this matrix into both the lower triangular. So one will be the lower triangular and the other will be the lower triangular, which is transpose. Yeah, so the upper triangular matrix is the transpose of the lower triangular matrix. So that means we have the same elements for the L and U. Yeah, so U will be the transpose of L matrix. So this is Cholesky decomposition, but this only apply for symmetric matrix, so that we don't learn that on detail. So this is just to make you know that we have a variation of the LU decomposition method. Okay. So then now we will continue to the iterative solution, in which this iterative solution is the one that you have applied in heat transfer. So have you get into this discussion in heat transfer about the topic of one-dimensional heat conduction or two-dimensional heat conduction on a plate?
We discussed it in 2 dimension, but we still not reached that one.
Oh, you haven't finished that topics, yeah? Not yet?
Not yet. Not yet.
Oh, not yet. Okay. So still ongoing.
Yes, ma'am.
Okay. So if you learn that, yeah, because this is on the same semester. So basically what you will learn in 2D heat conduction, yeah, on a plate in heat transfer. So that will be the application of the Gauss-Seidel method. Yeah, that will be the application of the Gauss-Seidel method. So what is the Gauss-Seidel method? Gauss-Seidel method is one of the most commonly used iterative method. Yeah. So with the iterative method, it means that we don't need to really construct the system as the matrix factor multiplication as what we have done before in Gaussian elimination or LU decomposition. So what we do in Gauss-Seidel method is that we reshape the system so that we solve the first equation for x1 and the second equation for x2 and the third equation for x and so on up to nth equation to solve for xn. Yeah. Okay, so what is the advantage of this method compared to LU decomposition or the Gaussian elimination is that the iterative method will be more rapid, yeah, so it will be faster, is the coefficient matrix is sparse. Yeah. So what is the meaning of sparse? Do you know what is the meaning of sparse? What is sparse? Terjemahan sparse apa?
Jarang mungkin.
Ya.
Betul, ya betul. Jadi terjemahan dari sparse itu jarang. So what does that mean if we have a sparse matrix? Yeah, so this is the term that is commonly appear in matrix. When we have a sparse matrix, it means that we have a matrix in which the element fills only several positions there. Yeah, so almost all of for example, the element here, yeah, almost all of the element is zero, except only in several element. Yeah, so this is sparse. So most of the element are zero. Yeah, jarang. And why it be more rapid? Yeah, because we will see later that iterative method is basically not storing, is not explicitly storing the matrix, because if we want to store the matrix, it's useless because most of the elements are zero actually. So that it will be more economical as well with respect to memory. So that means that we only store coefficient that has value, which is not zero. And this may also be applied to solve nonlinear system, such that what you learn, in 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 heat transfer, in which you will learn that, for example, you have an equations, in heat transfer, so that like that one. So that will be squared. So that will be heat conduction. So this will be heat conduction. So this we can apply that one in fluid in heat transfer problem. So this is the example of non-linear system as well. And it may not converge, or it, but the disadvantages is that it may not converge or may converge very slow. And this will not sometimes not appropriate for all systems. So we will see how is the procedure with the iterative method. Instead, we will start with here, with n equations to solve for n unknowns, Then we have the right hand side. So what we do to solve this one, so that we reshape the equation so that we can solve x1 from the first equation, so that we have x1 that will be equals p1 minus, we move all of the other terms to the right and then divide it by the coefficient of x1, so that we have p1 minus a1 2x2 plus a1 3x3 and so on, divided by the coefficient which is a1 1. And then from the second equation, we want to solve x2. So x2 will be equals to b2 minus a2 1x1 plus a2 3x3 and so on, which is all of the terms on the left hand side here. We just move to the right, and that is divided by a2. This should be a2, a22. So this is correct, a22. And then we find x3 from the third and so on up to xn. So when we want to calculate xn, so that will be calculated from bn minus all of the other terms, which is moved to the right-hand side divided by the coefficient of xn. So once we have this equation, so what we can do next is just only calculating these equations. So because this is an iterative method, so we will see here now for Gauss-Seidel method, which is the first method that we discussed. So the Gauss-Seidel method here. So we try with 3 by 3, or we have 3 equations to solve for 3 unknowns, so that we have x1, x2, and x3 from each of the equations. So this should be x3. And then we start with the first calculation, which is said to be the first iteration. The first iteration. So when we do the first iteration, so then we can calculate x1. So x1 will be equals to b1, which is the right-hand side, which is known, minus a12 times x2. Now the question is x2 and x3 here is not known yet. So where can we get this value? So that with iterative method, we always need initial values. We always need initial values. So what is the initial value that we use? We can use any value. But to make it simple, it's easy to choose that the initial value 0. So then with this initial value, we can assume that x1, x2, and x3 is equals to 0. All of that value are equals to 0. So that, here, when we don't have the value calculated yet, so that we can take this value from the initial value. So that from the initial value for the first iteration for x1, so that we have x1 is to a certain value. And then we want to calculate x2. Yeah. So when we calculate x2, so that we need the value of x1 and x3 in the calculation. In Gauss-Seidel method, if we have if we have the value already, so then we can use it directly. What if the value is not available? So that will be taken from the initial value or the previous iteration. Yeah. Okay, so then we have the value of x2. And then we can continue calculating to x3. Yeah, so how to calculate for x3? So that x3 will be equals to p3, we have the value, a1, a3, 1, we have the value, and x1 here, and x2 is already obtained from the calculation. So that we have x1, we insert the value here, x1, and then we have the value of x2 here into the calculation, so that we can calculate the value of x3. Yeah. So when we finish that, is this the final result? No, not yet. So we have to check for the error. Yeah. And remember how to calculate the error. So that will be if we have the true value, so we can directly calculate the true error. Yeah. But if we don't have the true value, so that we can approximate it, we can calculate the error by the approximate error. So how to calculate the approximate error? Do you still remember?
Recent calculation minus the previous calculation upper new calculation.
Yeah, yeah.
Only 100%.
Yeah, so over the new value. Yeah, okay, so that's correct. Yeah. So if we want to calculate the error, so that we can calculate this one. Yeah, so we have the error, the approximate error for x1. We calculate that. So that we insert the value of x1 here minus the previous value. What if we don't have the previous value? So the previous value was taken from the initial value. Yeah, so that we can calculate that will be minus 0 divided by the new value times 100%. So that will be the error of x1. Is that finished? Not yet, because we have 3 unknowns, so that we have to calculate the error for each of the unknown. Yeah, we have to calculate the error for each of the unknowns. So now we have to calculate the error for 2. Yeah, and then we have also to calculate the error for 3, x3. Yeah. So when it's still higher than the error, the level of error that we want to, so then we need to continue to the second iteration. Yeah. So how to do the second iteration is exactly the same like this one. Now the difference is the value of x2 and x3. Yeah, because we now in the second iteration, so that now x2 here is taken from the first iteration. Yeah, so that now become x1 for the second iteration. And then when we want to calculate the x2 value at the second iteration, so then what we have here, x1, is already calculated from the second iteration, yeah, so that we can use the new value from the current iterations. What about the x3 value? Because x3 value is not calculated yet, so we take that from the previous iteration. Yeah, so that we get the value of x3 from the value of the first iteration before. Yeah. So then x3 here, now we have the value of x1 and x2 from the first iteration, so from the second iteration already, so we can get the value. Yeah, wait for a while. Yeah, so that when we finish with the second iteration, and then we will calculate again the error. Yeah, and we want to calculate again the error. So that will be the value from the second iteration for x1, for example, minus the value of x1 from the first iteration divided by the value of x1 from the second iteration, and so on. Now the question is how to determine when to stop, when to stop. As I said before, when we can stop the iteration when it's already below the prescribed value. Now the question is what value? Because we have 3 value of the error here. So what value that we use? Now the easiest way is to find the maximum value, and then we compare that maximum value of the error of all of the unknowns here with the level that we want. So for example, I want it to be less than 1%. If I want to have it less than 1%, so then I will check for the largest error here. So it means that if we choose the largest error, it means that we are using the infinity norm. So back again to the norm that we learned last week. We have the norm of the factor, in which if we have the unknowns, if we have the error of the unknowns here, in which we can write down the error for x1, the error for x2, and the error of x3, and the error of x4, and we want to compare that with the error, for example, of our prescribed. For example, 1%. We want it to be less than 1%. So what is the factor norm here? So if we choose which one is the maximum, it means that we are using the infinity norm. So we choose the largest error, and then we compare that with 1%. So it means that it's already, if it's already below 1%, it means that we can make sure that for all of the other here, the error is also less than 1%. But sometimes in some software, it's not using the infinity norm. So if you look at, for example, in some finite element software or CFD software, sometimes it's not just using the infinity norm, but sometimes it's using the Euclidean norm. So it means that it will square the value of the error, and it do the summation and then square root it and see whether the result here is lower than 1% than our prescribed error. So this is how the correlation of calculating the error with the factor norms that we talked last week. Okay, back again in the slide. Okay, so this is the Gauss-Seidel method, and this is how the calculation of the error is performed, So that if we choose the infinity norm, it means that all of the maximum, the maximum error will be less than the prescribed error, or we can say that that will automatically means that all of the error for the value of the unknowns will be less than 1%, for example. Okay. So if we have more than 3, we have up to n, so then we can write it down as this one, So that if we have j, in which the superscript here denotes the iterations, so that if we have the iteration of j plus 1, so that the value that has been obtained before in the current iteration will be used directly. So for example, here we have calculate x2, so that will be equal to b2 minus a21 x1 plus a23 x3 and so on. So that if we have the value already updated in the current iteration, so that it will be used directly. So if we have calculated x1 at iteration j plus 1, so we will use it directly. While the value with which is not calculated yet in the current iteration will be taken from the previous iteration, and so on. So we see here that when we calculate x3, so that x1 and x2 have already been calculated, so that we can use it directly. While the other, which is not calculated yet, will be taken from the previous iteration, and so on, up to xn. So when we calculate xn, so all of the value of x here is already calculated, so that will be taken from the updated value. Now the second method here is called to be Jacobi iteration or Jacobian iteration. So this is the second method. So basically, this is similar to Gauss-Seidel. Now, The difference is that when it computing a new set of x, new x value, it's always on the basis of a set of old value. Yeah. So that what is the meaning? That as the new values are generated, yeah, they are not immediately used, so not used directly in the same iteration, but it is just retained, yeah, or saved, or yeah, we save it in the memory to be used for the next iteration. Yeah. So this is the difference between Jacobian and Gauss-Seidel. So we will see here that for the Jacobian method, if we have xi, x2 up to xn, and this is calculated for iteration j plus 1, so we can see here that when we calculate xi, so x2, x3 up to xn is calculated based on the value from the previous iteration, which is j. Once we have xi j plus 1, and then we want to calculate x2 j plus 1 at iteration j plus 1, so that the value of x1 here, although it's already updated in the current iteration, but it's not used directly. Yeah. So all of the value here is still using the old value, the previous value. Yeah. So it means that when we have the value, it is not used directly, but instead it is saved, yeah, and then will be used together. All of the set will be used together in the next iteration. Yeah. So it means that in a current iteration, it will use all of the value from the previous iteration and so on. So this is the comparison between Gauss-Seidel and Jacobian iteration. So we see here that during the first iteration, when we don't have the value, we will take that from initial value. And what is the difference when the value is updated in the current iteration? So we see here that in Gauss-Seidel, when we have the value updated, so it will be used directly in the next calculation in the same iteration. Yeah, so for example, this one, x1, already updated, so it will be used directly in the next calculation in the same iteration. Well, Jacobian, yeah, will use the updated value together later when we proceed to the second iteration and so on. So it means that although x1 is already updated, it is not used directly in the next calculation if it's still in the same iteration. Okay. Now, my question is, which one do you think will be faster?
Maybe the Gauss-Seidel method.
Okay, Gauss-Seidel method. Why?
Because the value for the result for iterating, the first iterating step will directly use map. So not waiting for the other, this will directly use, so it's maybe will faster.
Yeah, okay. Yeah, so yeah. So you are correct, yeah. Which one is generally will converge faster? So the Gauss-Seidel will converge faster because the value, the updated value will be used directly. So that means we'll make the convergence faster. Now the question is, if we have the Gauss-Seidel method already, why the Jacobian iteration is still used? Yeah. So the Jacobian iteration is still used. And if we talk about, the numerical method, this method is still popular. It's still very popular, although we have the Gauss-Seidel method. So we look here in terms of the calculation is similar, yeah? So we have exactly the same equations to solve it. The difference is only when we use the updated value. So why Jacobian method is still used? Because the answer is, this is dealing with parallel computing, yeah? So we know that nowadays we have a complex problem. We have very large system to be solved, millions of equations to be solved, yeah? Or maybe billions of equations to be solved. So that sometimes we are using parallel computing. So when we talk about parallel computing, that parallel computing can be use several PCs or even one PC with several cores. Yeah. So if we have one PC with, for example, 8 cores, so we can do parallel computing in that single PC. Yeah. So that what is actually parallel computing? So it's actually dividing the task, yeah, dividing the task to each of the processor. Yeah. So say we have one, for example, we have 3 million equations to be solved, and then we have 3 processors. It means that we will divide the task so that each of the processor will perform 1 million equations. Yeah. So if we have 3 million equations to be solved, so that we will divide it into 3 processors, so that each processor will need to calculate for 1 million of equations. So that in that case, Jacobian method will be chosen. Why? Because it means that when we divide the task to the processor, it means that each of the processor will keep calculating until it's finishing the task. And afterwards, it will do the communications with the other processor. So it means that the communication between one processor to another is it's occurring only when it changes the iteration. So it means that during the first iterations, yeah, all of the data has been divided, and then it will do the calculation, finding the value of x1, for example, up to x1 million for one processor, and then next, yeah, from 1 million one up to 2 million, yeah, for example, and the next, and so on. So it will calculate inside the processor itself. And when it's finished for that iteration, then it will have the communication to transfer the data. Yeah, because we see that there is a connection between the value of x2 and x3. It means that there will be a communication between some points, yeah, some variable here that needs to be exchanged from one processor to the other. So it means that the communications only performed at the end of the iteration, then it will proceed to the next iteration and so on. So in this case, why we still using Jacobian, particularly for parallel computing? So that means it will be faster. Because when we talk about parallel computing, the most challenge, yeah, that hinder the speed of the calculation is the communication time. So that if we can minimize the communication time between the processor, it means that we have faster calculation. So perhaps, yeah, in terms of convergence, how many iterations that will be needed, Gauss seidel will be faster. But when we talk about parallel computing, yeah, the addition of iteration, yeah, will be negligible compared to the faster calculation for each of this iteration itself. Yeah. So we can imagine if, for example, we use the Gauss seidel method for parallel computing, it means that communication will need to be performed every calculation. Yeah. For example, when we calculate x1, then we finish calculate x1, and then we need to do communications to calculate x2 and so on. So that will be quite slow. Yeah. So that's why Jacobian method here is still used. Yeah. Okay, so this is the convergence criterion for Gauss seidel as well as Jacobian. Is similar because both are iterative methods. So that is, if it has two fundamental problems, yeah. So it sometimes diverge or non-convergence, and if it converges, sometimes it converges very slowly. Yeah. So this is a problem with Gauss seidel method. All right. So then we will see the example here. Yeah. Say we have the same example as before. Yeah. So this is the same example when we discussing LU decomposition before, and also Gauss-Jordan. Yeah. We have the same example here, the same system. Now we want to calculate x1, x2, and x3. Yeah. So that with x1 here, so we have that to be say 7.85 plus, we move that to the right hand side, plus 0.1 x2 minus, so this should be minus, yeah. So this is a correction. So this should be minus, minus 0.2 x3 divided by 3. And then we have x2, the calculation of x2, that will be minus 19.3 minus 0.1 x1 plus 0.3 x3 divided by 7. Yeah. And then x3, we have 71.4 minus 0.3 x1 plus 0.2 x2 divided by 10. Okay, so this is the calculation. Now, we can calculate this one so that we need initial guess for the iterative method. So we choose 0 for x1, x2, and x3. So this is the initial value. And then we can insert it here to calculate x1, x2, and x3. Yeah. So x1, we get the value directly. x2 and x3 is taken from initial value. Once we have x1, and then we can use it to calculate x2 directly. Yeah. So we use the updated value directly here. What about x3 here is not calculated yet. So this is taken from the initial value, which is 0. And then finish with x2, we have the value of x2. And then now we can continue to x3. So x3 is 71.4 minus 0.3 x1. So this is calculated from here. We get the value already. And x2 is already updated as well. So we use it directly. And then we have the calculation of x3. Now we calculate the approximate error. So that will be 100%, yeah, for the first iteration. Now continuing to the second iteration, so that now for the second iteration, now we use that from the value of the first iteration, so that we use the value of 2.6167 here, yeah, and then for x3, so that one, yeah, x2 value, so that will be minus 2.7945. And for x3, we take that from the previous iteration, so that will be 7.115610. Once we have x1, now we use it directly. x3 is taken from the value from the first iteration. Yeah. Then we can calculate x2, which is this one. Yeah. So once we have x2 and x1, so that we can calculate x3, so that inserting the value of x1 here and x2 here, so that we have the value of x3, yeah, which is 7.000 and so on. So that now with second iteration, we have the error is already quite low. The maximum is still 12.5%. So if we want it to be, for example, less than 1%, so we need to continue to the third and fourth iteration and so on up until the maximum value of the approximate error is less than 1%. Yeah, so this is for the Gauss-Seidel method. Now, if we see that there is a problem with the calculation, with the progress of the calculation, for example, the error is reduced, but it reduced slowly. Or on other case, we have an error which is fluctuative. Sometimes it's low, and then sometimes it's getting up again, and then lower again, and up, going up again, and so on. So we have fluctuating, so that we can apply relaxation factor. So relaxation factor here is to improve the convergence rate. Yeah, to improve the convergence rate. So here we have the value of lambda, which is the weighting factor, that is assigned between 0 and 2, so that we can give a value of 0 and 2. So what is actually lambda, or the weighing factor? Some other book use omega, yeah, as a weighing factor. So what is actually the relaxation factor? So relaxation factor is that we give a weighing, yeah, we give a weighing between the new value and the previous value. Yeah. So for example here, when we calculate the value of x2, for example, we need the value of x1. Yeah, we need the value of x1. And what we've done here is that we take the value of x1 directly when it's calculated. Now, if we applying the relaxation factor, it means that when we use the value of x1 here, so that it's not using directly from this value. but then it's weighted with the previous value. So for example, we have x1, 0, which is the initial value. And then we have x1 at the first iteration. So that when we want to use x1 at the second iteration, so it's not directly calculated from this one, but instead is calculated by x1 lambda x1 plus 1 minus lambda, the value before. Yeah, so this is calculated. So what is calculated here is not used directly, but instead it is weighted with the value before. Yeah, so that we have a more stabilized value. Yeah, we have a more stable value here when we use it in the next calculation. Yeah, so we see here that if we have the value of lambda or the relaxation factor is 1, so it means that the method is unmodified. So if this is 1, so that is 1, so this will be 0. So it means that it's not using the old value. So it means that the new value, which is used, is directly from the calculated value. So this is what we have performed before. Yeah, so we use it directly. If we apply lambda between 0 and 1, so it means that is we applying the under relaxation. So it means that, for example, we take half, yeah. So that if we want to calculate xi new with half, so that will be calculated by xi new, which is calculated plus 1 minus lambda or minus half. So that will be half, yeah, of the xi old. So it means that if you want to use the new value, so that will be the average, yeah, between the calculated value, the new calculated value, with the old value, the previous value. So this is called under relaxation factor. So that this is particularly we can apply under relaxation factor to make a non-convergent system. For example, we have a diverged system, or for example, we have a oscillation or fluctuation in the error, so then we can apply under relaxation to make converge. If we have lambda between 1 and 2, yeah, for example, 1.5, so this is said to be over relaxation. Yeah, so if we, for example, apply 1.5 or 2, for example, if we apply 2, so that xi new will be calculated by 2 times of xi new plus 1 minus 2, so that will be minus xi old. Yeah. So that means we exaggerate the way of the new value. Yeah. So that is over relaxation. So this can be used to accelerate the convergence. But be careful with that. Yeah. Be careful with over relaxation, because sometimes it's not acceleration that we get, but sometimes it also makes the convergence slower. And this is very rare to be performed, yeah? So it's very rare that we need to apply over relaxation. Most of the time we need to apply under relaxation, because when we have a complex problem, yeah, the problem is that the system will be quite difficult to converge or fluctuating. Yeah, so that in that case, it's more common to apply under relaxation factor. So be careful with over relaxation factor. Yeah, very, very careful with applying over relaxation. Okay, so we will see the example here in which we have the second example. Yeah, and we see in this example later that we will apply relaxation factor. Okay, so we have this case. We have 3 equations. Yeah, to find for 3 unknowns, x1, x2, and x3. Now, as a general rule, yeah, if we have a set of linear algebra, yeah, as a general rule, if we want to have the calculation faster and we want to reduce the round of error, such as step in Gaussian elimination or Lie decomposition, is that we need to rearrange, yeah, we rearrange the equation so that it will become diagonally dominant. So what is diagonally dominant is when we have the matrix and the largest value will fill in the diagonal element. So this is called diagonally dominant matrix. So that when we have this equation, we want to rearrange so that this equation will be diagonally dominant. It means that we choose the maximum value to lies in the diagonal element. Okay, so we see for the first equations, we have -8, so that is already diagonal dominant, yeah? -s plus x minus 2x3. And then here we have the largest value is here. And here for the third equation, we have the largest value is -6, so that we switch the rows here. Yeah, so that it will become diagonally dominant. So this is a general rule. If we want it to be converge faster, yeah, and the round of error will be smaller. Yeah. Okay, so we rearrange these equations, or usually in Gaussian elimination, we set that to be partial pivoting. Yeah, we do partial pivoting. So this applies as well in the iterative method. Yeah, we want it to be diagonally dominant. Okay, so once we have that diagonally dominant, so that now we can calculate x1. Yeah, so that x1 here will be calculated from -20 minus x2 plus 2x3 divided by -8. Then for x2, now we calculate by -38 minus 2x1 plus x3 divided by -6. And then for x3, we have -34 plus 3x1 plus x2 divided by 7. So that here we have the equations. Now we can do the iteration. Okay. So this is the iteration. So that now we apply for the 0 iteration, which is initial value. We give all 0 value for x1 and x2 and x3. And then we calculate for the first iteration for x1. Yeah, so that we insert the value of 0 here and 0 here as well. So once we have the value, we can insert it here. And x3 value is taken from initial. Once we have the value of x2, we can insert it here and also x1 here, so that we can calculate x3. So that the value from the first iteration will be this one, with the error 38%, 12, and 42%. So this is for, sorry, this one, yeah, first iteration. With the second iteration, we can apply the same. Yeah, now we insert the value here from the previous iteration. Yeah, so this is taken from x2 from the first iteration and that one from the first iteration. Now we use the updated value directly so that we can calculate x1, x2, and x3. And the error is already reduced. Now the third iteration, we do the same. Now the error is already below 3% with a maximum error of 2.92%. So it's already below 5%. Okay, so we will now see the same example with over relaxation. Yeah, it means that we have a factor here, a weighing factor greater than 1, which is 1.2. So we do the first iteration using the value from initial value. So then we have the value as 2.5. Now, because we are applying relaxation factor, it means that this value is not used directly, but instead the new value here is calculated by lambda of the new value plus 1 minus lambda, the old value. The old value, yeah. So that here we have, for example, we want to calculate x1, so that will be 1.2 of x1 new value plus 1 minus lambda, so that will be 1.2 of the old value, so that will be x1 0. So that we will have 1.2 times 2.5 plus, this is minus 0.2 times x1, the old value, which is 0, initial value. Yeah, so here we have 3. Now, if we have calculated this value, the new value, so that now we can use it as before, yeah, so as the regular calculation. Yeah, so the difference is only this one. Yeah, when we want to use the value, so that we have to apply the relaxation first. So we are not using directly this value. Instead, we calculate it with the relaxation and then we insert it here. Yeah. So then now we have the new value for x2 from this calculation. When we have x2, so that we don't use that directly, again, we apply this one. We apply a relaxation factor so that we get a weighing of 1.2 times x2 new value minus 0.2 times the old value of x2, which is the initial value. So that now we have 8.8. So now that is the value that we use. Yeah. It means that the value that is used is the updated value with the relaxation factor. So that we have x3, and again, x3 is relax first, calculated with relaxation first, so that we have the value. So then we can use all of this value here later for the second iteration and so on. So this is the final value. Yeah. So the the value with the relaxation factor is the result. Yeah. The result that we have. So that we have here that from the first iteration, the value with the relaxation factor will be here. So this is the final value. Yeah, the final value that we use. So we can see here that we have an error. So when we calculate the error, is the error when it's already calculated with the relaxation. So it will be here. Yeah. So when we calculate, the error is here. So this is the result. Yeah, not this one. So this is only the calculated value. Yeah, this is calculated value, but the final value, yeah, is this one, the value with relaxation. So we see here that when we apply relaxation factor, in which we want it to be faster in convergence, we see here that up to 4 iterations, the maximum error is still 19%. So we see that the basic method, the basic method without relaxation factor with 3 iteration is already below 5%. Now with over relaxation, instead of getting the convergence faster, we have it to be slower. Yeah. So we see that we have now up to 4 iteration, the error is still 20%. So in this case, we've seen that in this, the over relaxation method here is failed to make the convergence faster. Yeah, so please be careful when we apply the over relaxation factor. Yeah, but under relaxation factor, yeah, we can use it when we have divergent solution, yeah, or when we have fluctuation in the calculation. As a general rule, if we do the calculation and there is nothing, there is no problem with the calculation, so we can use unmodified method of Gauss cycle. So we can just choose directly the value which is calculated. Yeah. Okay. So that is about Gauss cycle method. Any question?
Excuse me, ma'am. Can I ask?
Yes, William.
Does it mean when we have divergence function, it must be under relaxation, ma'am? And for the converse function, it means that we have to check whether using the basic or the over relaxation, ma'am. We have to check it again.
Yes. Under relaxation, yeah, we can apply that when we have divergence. Yeah. Okay. So when we have divergence result, we can try with several alternatives to make it converge. Yeah. So the first one is try using under relaxation, but this is not the only way. Yeah. So sometimes if we have singular problem, as we learned before, yeah, there is some cases in which we have an equations and there will be no solution, yeah, or there will be infinite solution, yeah, as we've seen with that. So in that case, if we have that sort of system, we cannot find the solution as well with Gaussian elimination, or even LU decomposition, or even Gauss cycle. So in that case, the problem is with the set of system, the set of equation. Yeah. So it means the problem with the set of the equations. But if so then in that case, yeah, it will be diverged as well when we test it with Gauss idle. But there is nothing we can do because the problem is that the system itself has no solution. Yeah. So in that case, if we try to change the under relaxation factor and it give no improvement, it means that it can be that the system itself, which is singular system. Yeah. So that means there is no solution for that case. Yeah. So in that case, changing the under relaxation will give no improvement as well. Yeah, because the problem is with the set of equations of the system. Yeah. But if, for example, we have a system which is actually can obtain a solution using Gaussian elimination or Lie decomposition. Yeah, it has a solution. Actually, the problem has a solution. But when we apply Gauss-Seidel, because iterative method is more prone to divergence, yeah, it can sometimes lead to convergence. It means that the problem is not with the system. The system is okay. It has a solution, but the problem is with the method because we're applying iterative method. So in that case, if because of the iterative method, so this is dealing with iterative method, so that we can apply under relaxation. Yes, we can try to apply under relaxation so that it will give, it will avoid divergence or make a convergence faster. Yeah. The other way is, aside from applying under relaxation factor, is that to choose better initial value. Yeah, to choose better initial value. So we have seen in many cases that if we have initial value that is closer, yeah, we have initial value that is closer to the to the results, yeah, closer to the results. So that will make a convergence faster. Yeah. So there is two way dealing with divergence or slow convergence. Yeah. Is to choose different under relaxation, to apply under relaxation, or to choose better initial value. Yeah. So that will be the answer for the first question. Yeah. And the next question, what is the second question? Can you repeat?
I just make sure, ma'am. So the under relaxation is just only for the divergence function. It's like for the convergence function, it's not necessary to use under relaxation because it have converge solution.
Yeah. So if we have a convergence, yeah, if we have a converged solution, so we don't need to apply under relaxation at all. Yeah. So because under relaxation, if we apply to say a converged solution, this will make slower as then. Yeah, make slower. So if we have a fine just a fine calculation, and then we want to apply under relaxation, so that makes slower. Yeah, it'll make the calculation slower, the convergence slower. But if we have fluctuation, yeah, so we have fluctuation. For example, we applying the error, yeah, we applying the error, plotting the error with the iteration, for example, yeah. And then we see that the error is fluctuating like this one, sometimes going up and down and so on, so that we can make this stable, yeah, by applying under relaxation. Yeah, so that will stabilize the calculation, because we see here that it's fluctuating because the value is quite large difference. So if we have under relaxation factor, so that it will give some damping to the fluctuation. Yeah, it will give sort of a damping function. Yeah, damping to the fluctuation, so that it's not the value will not change a lot, because we take the average value. So it means that when the new value is low, very low, and the old value is very high, so that it will take the average value, yeah, in to be the updated value. So it means that this will stabilize the value, yeah, or damping the fluctuation. Yeah. So that is about under relaxation factor. But if the calculation progresses very well without any relaxation factor, so that you can use without relaxation factor. Yeah. Okay, is that answering your question, William?
Can I ask for last question, ma'am?
Yeah.
So if
Yeah.
we try to using, for example, in the Gauss-Seidel method, example 2, using another value of weighting factor,
Yeah.
it will result the same, ma'am, that the converge will be slower.
We can try, yeah. So there is no guarantee as well that it will be slower or it will be faster, but we can try, yeah. So do some testing, yeah. We can do some testing with different weighing factors. So you can try any. It's not always, yeah. There is no exact value which one is correct, so that we can try with, for example, 1.2, or we can try it 1.4, or we can try it with 0.8. Sometimes it can be faster, yeah, as well. But yeah, the only way is by testing it. Yeah, the only way by testing it. But again, yeah, the weighing factor here, if the problem can converge, yeah, if the problem can converge, so that the weighing factor will not affect the accuracy, yeah. The weighing factor will not affect the accuracy, because at the end we will check whether it will reach to a certain approximate error that we want, yeah. So it means that the final result will not be affected by the weighing factor. Now the difference with the weighing factor is how many iteration that will be needed. Yeah. So it means that if you applying 0.8 or 1.2, at the end you will have the similar result. Yeah. When we prescribing the approximate error that is similar. Yeah. But the number of iteration that will be different. Now you can try with 0.8, perhaps it will perhaps few iteration faster or few iterations slower. Yeah, but the final result will be the same. Yeah, as long as we applying the same error, the same level of error. Yeah. Okay. So yeah, it's quite difficult to say what is the best weighing factor. So this depends on the system itself. So we can do some testing with that. Yeah.
Okay, ma'am. I think it's very clear. Thank you.
Yeah. Okay. Thank you. And you were asking about over relaxation, if I'm not mistaken, isn't it?
Yeah, just before this question, ma'am, I just make sure that how about the weighting factor?
Oh yeah. So you can use any value. Yeah. So
Yes.
it's free. In some software, so for example, you have finite element or CFD software, you can set this value as well in the software. Yeah. So there is no guidance as well of what value should be taken. Yeah. So in general, if there is no problem with the calculation, you can use just the unmodified method. Yeah. But if you see later in the calculation progresses, so that you see there is a fluctuation or very slow to converge, so that you can consider to change the value. But overall, this is not affecting, not affecting the result, in general. So as long as we have the same level of error prescribed, that we want, so that, it will only make the convergence faster or lower, like that. Okay. Okay, so this is about relaxation factor. Any other questions?
Not yet, ma'am.
Yes. Okay. So we see now the comparison. Yeah. So Gauss-Seidel will converge faster than Jacobi, as we have discussed before. Now, why we still using Jacobi? Why we are still using Jacobi? Because this is suitable for parallel computing. Okay, so that this is about the convergence. So I think we will see the the comparison here between the direct methods or elimination method, as in Gaussian elimination or LD decomposition. So basically it's require of the order of n to the power of 3, which is n is the number of unknown or the number of equations. While iterative methods, it's never explicitly stored a matrix, so that if we have a sparse matrix, so that will be a saving of memory. And also when we calculate, so it will be faster. So it will be faster when we do the calculations. So we see here that at worst, so this depends on the number of iteration as well, but at worst it will be of the order of squared n. It means that it's only squared n. Well, what we have in Gaussian elimination is at the order of n to the power of 3. So that we see here that the memory requirement, and also the number of floating points operation needed, is less. Although we do repeating calculation, although we do repeated iteration, many time iteration, but still it will be still less flops needed compared to Gaussian elimination. So that's why when we talk about numerical method which is applied in software, for example in CFD or finite element methods, most of those software are using iterative methods. So, but it's not usually it's not the Gauss-Seidel method. So it's using more advanced iterative methods. So you will learn later if you are interested in that. There is some other improved version of iterative method, like P conjugate gradient method, and so on. So there are many further development from the iterative method. So it's basically not only 2 of these. So this is just a very basic iterative method. So we have more advanced, improved method relates to iterative method, which is applied in the numerical software. So that about the set of linear algebra equations, for the solution, we have learned the basics of that, and that we can also use Excel. So this is the application of what we have learned. So in Excel, you can also find the inverse of the matrix. You can find the inverse of the matrix. So say you write down the element of the matrix A here in these cells, in these cells. So you can try that. Fill in this element in the cells, and then the B vector, which is the right-hand side vector here, the right-hand side here. And then you can find the inverse of the matrix. So how to find the inverse of the matrix? First, you have to block the cells, which is the size of the inverse of the matrix, so that you have to block 3 by 3 cells like this one. And then you type the function to find the inverse. So the Excel software have the built-in function, the function in Excel in which this will calculate the inverse of the matrix. So M inverse here will calculate the matrix. So we insert that M inverse from B1 up to B3. So 3 by 3 matrix. So this is the size. And then when we press enter, don't forget to press Control and Shift key together. So we press Control and Shift keys together, and then we press the enter. So that means 3 keys pressed together. The Control, the Shift, and the enter key. So this to make sure that it's filling all of the cells here, not only one cell. Because if you press enter only, so it will be only filling one cell here. But to make sure that it will fill all the cells here, which is from B1 up to D3, from B5 up to D7, so that you have to press Control and Shift keys together when you press enter. So that we will have this result, and then we can find the X value, the unknown factor, by multiplying the inverse with B. the right hand side. So multiplying that, we block the cells first here, and then we type M multi, which is the matrix multiplication. And then in the bracket here, we choose first here is the inverse. So that from D5 up to D3, so we just block that matrix. And then we give comma, so that will be the multiplication with second matrix or the second factor. So here we choose the factor, which is the right-hand side from F1 up to F3, and then we press enter. Again, when we press enter, don't forget to press Control and Shift keys together. Yeah, so that it will fill all of the cells that we block, not only the first cell. Yeah, so you can try that. Yeah, you can try this one in Excel. Now you can try it now. Yeah, so you can open Excel. Yeah, you can open Excel now, and then you can insert the value there. Yeah, in the matrix. Yeah, you can try to open Excel. Yeah, so we write down the matrix of 1. For the first row is 1, 0.5, and 0.333, for example. Yeah. And then we have 1. Or you can insert directly here, half, yeah, 1/2. And yeah, that will be 1/2. Will be 1/3, yeah, and so on.
Ma'am, excuse me, ma'am.
Yes.
When we push Control Shift and Enter together.
Yes.
When
we want to press enter, yeah. So when we block that, so I will start this one, yeah. So when we put the matrix A here, and then what we do here is that we block the size of the inverse, yeah, and then we type M inverse, and then we choose the array to inverse, the matrix to inverse. And then when we want to press enter here, yeah, we want to press enter, so that we press Control Shift first, Control and Shift together, and then we press enter so that it will fill all the cells. If we don't use press and key, so it's only filling one cell only, yeah. So say I'll just do the regular one here, like this one, and then just press enter, so it's only fill the first element, the first cell, yeah. So that you have to make sure when you pressing that, you have to press Control Shift and then enter.
Oh, okay, ma'am. I already did it, ma'am.
Okay.
Thank you, ma'am.
Okay. And again, when you do multiplication, so there is a mistake, yeah. So it should be and here we see that it should be dot comma. So the slide is only comma, yeah. So it should be dot comma because the multiplication function here should be with dot comma. So you can try that one. Sorry. I will erase that. Yeah. So that when we choose the cell as a result here, the factor, so that we try and multi, and then choose the first array, which is the inverse of the matrix, and then dot comma, yeah, dot comma, and then inserting the factor of the right hand side, and then we again pressing Control and Shift together with Enter so that we have the result. Yeah. Okay. So all of you have succeeded to try this one.
Yes, ma'am.
Okay. Okay, so this is how to find the inverse, yeah, in Excel, and then you can you can use the inverse to multiply it with the right hand side to get the unknown. So how is the procedure to get the inverse? So what Excel did is using one of the methods that we have learned before, yeah, on how finding the inverse of the matrix. So if you have a large matrix here, you can try it with 10 by 10 matrix, for example, you can find the inverse as well using Excel. But at least now you know how Excel did it, yeah, how Excel did it. So it's using the algorithm from the numerical method that we have learned before, yeah? So we have Gaussian elimination, we have Gauss-Jordan, we have LU decomposition, and so on. Okay, so now I will return to the slide here. Yeah. So here is the revision is that here is with dot comma, yeah, because the function is with dot comma here. So it's not only comma, yeah, but with dot comma. Okay. And also in MATLAB, yeah. So in MATLAB, you can use functions to implement matrix analysis. Yeah, so you can find the condition number of a matrix. You can find the norm as what we have learned before. We have several norms to calculate the matrix, and we have for example, many functions related to matrix analysis. And for the solution for linear equations, we can use backslash or forward slash like this one. Yeah. And we can use Hall here for Cholesky factorization as what we learned here, which is Cholesky is only for symmetric matrix. And we can also get LU, which is the factors from Gaussian elimination. Or if inf, yeah, so this is a function to find the inverse of the matrix, or QR, so this is another method, yeah, which is also iterative method, in which we don't learn about that at the moment, yeah. So there are several functions which is available for a solution for a set of linear equations and also for matrix analysis. So you can try that on MATLAB. Yeah. So you can, if you have MATLAB, you can try to open it. Yeah. So that we can try using the same matrix that we have before. Yeah. In MATLAB. Yeah. So that yeah, so I will try to share here. I don't have MATLAB, but I have Octave, yeah. So here is Octave. So it's pretty much similar. Yeah, I will try to make it smaller so that I can see the problem. Yeah. So this is Octave, similar to MATLAB. You will see sort of similar interface for the windows here. So that we can type the matrix A. Yeah, the matrix A here. So the matrix A, I will type down the matrix. So that will be with the square bracket. And then we insert the first line, for the first row. So this will be the first row. So I will insert it similar to what we have wait, I will move that to the right so that you can see. Yeah, so that we will insert this value 1/2 and 1/3. So this, if we have, where does it stop? Okay. Yeah, so if we have this one, when we separate a number with a space, so that will be the column. Yeah, and then we give dot comma, so that will be the end of the input for that column, for that row, and then we continue to the second row. Yeah, so after dot comma, that will be the second row. So 1, 2/3, and 2/4, and then the third row that will be 1, 3/4, and 3/5, and then we give close bracket. So this will be the result. Yeah, so you can check whether the matrix here, which is shown, which is saved in MATLAB or Octave here, is already correct. So then we can continue to insert the value for the factor, which is the right hand side. So we will type down the factor here. So that will be equals to 1 plus half plus 1/3. And then the second row, so that we make dot comma, so that means this is the end of the first row. So then we insert the second element, the second row. Then we give dot comma, and then we use the third row. Yeah. So then we can check the result, whether it's already correct, so that we have the B factor is already correct. Yeah. So that we can do, we can find the value. For example, for matrix analysis, we want to find the condition number of A, for example. Yeah. Okay, so that will be 366.35. So this is quite high. It means that is a little bit ill condition. Yeah. And then we can also find the result of the unknown, which is X. Yeah. So the result of the unknown, which is the factor X. Yeah. The factor X here. So how to find the factor X, so that we can apply that, we can find the value of X by augmented A with B. So that when we have a backslash here, this means that we augmented A with B, so that we have the solution of X. Yeah. So that to find the solution of X, that will be X, that will be equals to A backslash B. So that we augmented a matrix A with the factor of the right hand side B, so that we have the result X. So X here is the result. Or we can also find the inverse of A. Yeah, say we want to find the inverse of A, so we can type that inverse. So that here we have the inverse. So that we can also find X from the multiplication of the inverse of A multiplied by B. Yeah, so that we have the value of X. So that the value of X, whether we do augmented here, such as in Gaussian elimination process, that will be similar to what we have when we calculate the inverse matrix first and then multiplied by B. We have LU as well, so we can find LU. Yeah. So that with LU here, we have this value. Yeah, so when we have the value of A, so that means that the upper value here, when we have LUA, here the matrix is full, yeah, only one matrix, but it's full. So what does that mean? It means that the upper triangular here will be the upper matrix, and here the lower here, yeah, the lower part here will be the lower matrix, but we have to add 1, yeah, like that. So that will be, this one will be the LU matrix, which is stored together, yeah, which is stored together. So actually, this is stored together, but actually the upper matrix, yeah. So if we have like, sorry, how can I annotate that? I'm sorry, I will write it down here. How to show this? Yeah, so that if Yeah, so if we have this one, so here we will, can we add on it? Yeah, okay. So if we have this one, so that we will have this one here to be the upper matrix, yeah. So that will be the upper matrix, U. And for the lower matrix, so that will be filled with this one, yeah. So this is the lower matrix, plus the diagonal will be all one, yeah. So the diagonal will be all one, like that. And then we have 1, 1, 1, and 0.66667, while the other is 0. Okay. So this is how to put together LU as a single matrix. Yeah. Okay. All right. So with this, we can use MATLAB, or also we can use yeah, we can use Octave, yeah, to do the analysis. Now it's very easy to use that in software. But again, yeah, what we actually learn in numerical method is basically understanding how this software works. So what happens behind this is what we have learned. Yeah, so you can do it easily using software actually, yeah, but you have to understand how this software works. Okay, any question?
Ma'am, excuse me, ma'am.
Yes.
I want to ask something about the first of all is I want to ask about a condition, what the meaning of condition, and you was said that the it in C condition, a little bit of C condition, ill condition, I'm sorry. How to get that answer, ma'am. And then the second one is LUA, the last one you mentioned there.
Yes.
I still don't understand what the meaning of LU.
Yeah. So LU here is the LU decomposition. Yeah. So that means the LU decomposition. So that we can, as what we have before, we can decompose A into matrix L and U. Yeah. Yeah. When we have matrix A, so that we can decompose matrix A into L and U. Yeah. So when we have L and U, is actually we have that one. Yeah, L is filled with 0 here, and the element here is 0. Sorry, 1 like that one. The other is 0, and then we have L 2 1, L3 1, and L3 2 like that one. And we have U, yeah, the upper triangular matrix as what we learned before. So the value here will be 0, and this one is obtained from the Gaussian elimination. Yeah, U is here is similar to what we have in Gaussian elimination, but L here is a vector to make that 0. Yeah, we have learned about that before. Now it's very common in software to store that together. Yeah, to store that together as a single matrix. So how to store that? So it means that the U matrix here is stored here. Yeah, and the L here is filling only 3 element here, so it will be here. Yeah, well, the one value here is not stored, because we know when we have a lower triangular matrix and LU decomposition, so the diagonal element will be 1, so that we don't store the value of 1 there. So actually here what we have here, upper triangular here is the upper matrix, and the lower element here will be the lower triangular matrix here, which is added with 1 in the diagonal element. Okay. So this is basically finding the matrix of L and U for LU decomposition. If we need to find the value of that, if we want to find the decomposition of a matrix A, yeah. So this is just an example. Yeah.
Oh, okay, ma'am. So the diagonal for the upper matrix is not 1, ma'am. Right, ma'am?
The diagonal of the upper matrix
Because you said that the upper triangle in this matrix and LUA is all in upper matrix. So the diagonal is not 1, right, ma'am? For the upper.
Okay, so the diagonal here, wait, I will close this one. So the diagonal here is 1, isn't it? What do you mean? Can you repeat it? So we have this matrix, right?
Gini Mem, pakai bahasa Indonesia aja.
Ya,
Mem.
ya. Oke.
Jadi kan tadi yang LUA itu kan apa upper matrix sama lower matrix dijadikan satu matrix itu kan tampilannya. Nah, terus kata ibu tadi yang segitiga bawah 3 matrix itu yang lower, terus diagonalnya 1. Nah, terus sisanya kan ada berapa tadi? Ada sekitar 6 matrix yang di atas, 6 bilangan yang di atas, yaitu apa? Yang ini 1, 0,5, 0,3, 0,25, 0,26 sama minus 0,1 ini adalah uppernya. Nah, berarti kalau misalnya ini berarti diagonalnya nggak 1 dong. Berarti
Iya. Jadi begini, untuk menghemat memori ya, jadi biasanya memang diletakkan dalam satu matriks ya, L dan U itu diletakkan dalam satu matriks. Memang diagonal satunya nggak masuk begitu. Jadi dalam hal ini yang disimpan, coba saya kembali lagi ke sini ya. Jadi yang disimpan itu memang hanya U. Kalau U ini sudah jelas ya, U-nya ini sudah jelas. Nah, untuk L ini yang disimpan seharusnya kan L matriks itu tadi isinya 1, 1, 1 begini ya. Terus ini ada L21, L31, L32 begitu. Nah, memang yang ini tidak disimpan. Yang disimpan hanya ini saja. Karena apa? Berdasarkan pemahaman kita bahwa L itu memang hanya satu saja isinya di diagonalnya gitu. Jadi satunya ini tidak disimpan begitu. Jadi yang disimpan hanya L21, L31 dan L32 begitu. Nah, mana satunya? Ya satunya berdasarkan pemahaman kita gitu. Makanya artinya kalau kita mau menggunakan MATLAB ini kita harus punya pemahaman apa itu LU decomposition gitu ya sebelum kita bisa menggunakannya seperti itu. Ya jadi memang satunya ini tidak disimpan. Harusnya kan isinya 1 ya ini ya, yang lainnya 0. Nah, satunya ini memang tidak disimpan begitu. Jadi yang disimpan hanya L21, L31 dan L33, L32-nya. Begitu.
Oh, okay, ma'am. I get it, ma'am. Thank you very much, ma'am.
Ya, oke. Baik, silakan kalau ada pertanyaan lagi. Is there any question? Okay. Okay, so if there is no question, so that that will be the end for the set of the solution of set of linear algebra equations, and that will be the material for the midterm exam. Yeah, so the material for the midterm exam, like here, yeah. So that will include for the midterm exam that, yeah, in general, what we have learned before, which is about introduction, yeah, in which we learn about the error, which is we have round of error and truncation error. And dealing with truncation error, we have learned about Taylor series expansion. So this is an introduction. And also we have learned about roots of equations. Yeah, roots of equations, in which when we talk about roots of equation, we have the open and close, open and bracketing, yeah, bracketing and open method. Bracketing and open method. And with bracketing, we have two methods, yeah. Bisection, yeah. And what are the others?
False position method.
Yeah, false position method. And for the open method, we have two methods as well. What is the method?
Second method and Newton.
Yeah, second method and Newton-Raphson method. Yeah, and we have now discussing about set of linear algebra equation. Yeah, in which we have Gaussian elimination, we have Gauss-Jordan in general, yeah, we have Gauss-Seidel, which is an iterative one, and we have Jacobi. Yeah. So that will be the topic that we have discussed, and this will be the material for the midterm exam. Yeah. Okay. So for the midterm exam, again, I will let you know when will be the schedule. We were still discussing with the other lecturers on when, yeah. But if you say we still have on Wednesday, is there any objection because it's public holiday?
Afternoon.
If we still doing it in Wednesday, is there any objection? Ada yang tidak bersedia atau mungkin berhalangan pada saat tersebut pekan depan? Ini nanti kita diskusikan lagi ya. Seharusnya memang libur, cuma mungkin ini belum tahu kita nanti bagaimana keputusannya ya. Apakah kemarin ada usulan untuk tetap dilaksanakan pada hari yang sama begitu ya? Artinya tidak libur begitu ya? Atau dipindah ke hari yang lain begitu ya? Ataukah dipindah ke hari Sabtu begitu? Nah, ini masih kita diskusikan, tapi seandainya misalkan tetap Rabu begitu ya, jadi di hari libur begitu, kira-kira bagaimana? Saya usahakan tidak ya, saya usahakan tidak, tapi kalau misalkan ternyata nanti keputusannya begitu ya, artinya kan kita akan melakukan bersama-sama itu. Kira-kira bagaimana kalau Rabu depan? Ada yang sudah ada agenda lain?
Sejauh ini yang ada yang mau ada agenda itu cuma kuis 2 elemen sih, Bu. Elemen mesin 2.
Elemen mesin 2 itu kapan?
Hari Rabu minggu depan jam 7.
Oke, berarti tetap diadakan pada Elmes kan mestinya pagi tadi ya?
Iya kan?
Berarti artinya tetap diadakan pada hari tersebut ya?
Iya, kemungkinan seperti itu. Cuma nunggu kepastian 2 kelas aja kan, kata Pak Alif.
Iya, nah sepertinya begitu. Sepertinya karena ini online ya, kebanyakan itu dari dosen-dosen inginnya tetap berjalan seperti biasa begitu. Ya, jadi meskipun itu libur nasional itu kemarin dari hasil diskusi kita itu sepertinya kok akan diadakan ya, dari kemarin hasil diskusi itu akan diadakan tetap di jam yang sama. Jadi kalau misalkan hasil nanti diskusi itu ternyata keputusannya adalah hari Rabu, mudah-mudahan tidak ada masalah ya berarti ya. Kalau hari Rabu kembali jam 10 ya, karena jadwal awal kan memang jam 10. Begitu.
Oke.
Ya, jadi kalau tidak Rabu berarti pilihannya ke Sabtu begitu ya. Jadi sebetulnya sama aja, sama-sama liburnya gitu ya. Sabtu kan juga libur gitu. Jadi ya nanti kita diskusikan lagi begitu ya untuk kepastiannya. Tapi ya sebagai jaga-jaga mungkin bisa disiapkan slot kosongkan dulu ya untuk pekan depan hari Rabu jam 10 begitu. Karena ada kemungkinan kita akan mengadakan UTS-nya itu tetap pada hari Rabu pekan depan seperti itu. Ya.
Oke, Ma'am.
Oke, baik. Untuk yang lain bagaimana? What about the others?
Kurang lebih aman, Bu. Sama seperti Sultan.
Oke, baik ya. Ya, karena memang kalau mau mundur lagi kita nanti yang kerepotan ya, ngatur jadwalnya itu yang agak padat begitu. Ya. Baik. Jadi kalau memang tidak ada halangan ya, kemudian tidak berkeberatan untuk tetap Rabu ya, kita mungkin akan laksanakan tetap Rabu begitu ya. Nanti saya diskusikan lagi dengan kelas yang lain ya, karena rencananya nanti akan paralel juga untuk ujiannya. Jadi materi up to today ya, up to today. Okay, so that so that will be the end of the class. Now before we finish, I will give you a homework assignment. So I will give you an assignment here. Which one is that? Okay. So this will be the assignment. Yeah. For you to work on this. So this is there is a pump. Deliver highly viscous fluid at rate of 1 Q1. So this is the flow rate of the pump here, which is 8 liter per minute. Yeah, 8 liters per minute. And we see here that it will flow the fluid at several branches like this one. Yeah. So here from key 1 to key 2 and key 3 and then to key 4 and key 5 and so on. Yeah. And then we want to find the mass flow rate for each of these. Yeah. And here we assume that every pipe section has the same length and the diameter, so that here we assume that the pressure drop will be more or less similar. And the mass and mechanical energy balance can be simplified to obtain the flows in every pipe, so that here we have this set of system. Yeah. So the system here is already provided. Now, the question is how to find the flow rate here for each of the pipe there. Yeah. So here we have 7, 1, 2, 3, 4, 5, 6. Yeah. We have 6 equations. Yeah. We have 6 equations. Is it? Yeah. 6 equations. Yeah. To find for Q1 up to Q7. Yeah. Solving Q1 up to Q7. Now Q1 is already known here. Yeah, so that we have 6 equations to find from Q2 up to Q7. So this means that we have 6 equations to find 6 unknown for Q2 up to Q7. Now, we want to use 3 methods: Gaussian elimination, early decomposition, and Gauss-Seidel. Yeah. So that we will compare the result. Yeah. And for Gauss-Seidel, you can use any for minimum. So I will add this, that the error, the approximate error, less than 1%. So, and for the initial value for the Gauss-Seidel, you can choose any. Yeah, you can choose 0 or any value. Yeah, with the approximate error less than 1%. Now here is the hint to make the convergence faster and to make the round of error smaller. Yeah, rearrange the equation so that the system is diagonally dominant. So that when you want to calculate using any of these, try to rearrange the equation first so that it becomes diagonally dominant. Yeah, so that will make the calculation faster and reducing the round of error. Okay, so that will be the homework. Yeah, that will be the homework. And yeah, it should be submitted by tomorrow. Yeah, it should be submitted by tomorrow at 7 o'clock in the morning. Yeah, so you should finish this tonight. Okay, so this will be the assignment. Yeah, we still have about 30 minutes. Yeah, so if you can do some of that work as well. Yeah, so that due tomorrow morning at 7 o'clock. Yeah. Okay, any question?
Excuse me, ma'am.
Yes.
For Gaussian elimination, kan di situ ada berapa metode. Kita milih terserah ya, ma'am. Boleh Gauss Jordan, boleh yang naive Gauss, boleh yang mana gitu.
Gaussian elimination. Ya, jadi kalau Gauss Jordan namanya Gauss Jordan. Kalau ini Gaussian elimination, berarti Gaussian elimination dan di sini sudah rearrange ya. Jadi sudah pivoting sebetulnya. Ya.
Oh, oke, ma'am.
Oke. Jadi Gaussian elimination itu yang paling sederhana ya, yang paling awal, bukan Gauss-Jordan. Ya. Yang hasilnya nanti hanya upper triangular saja. Ya. Okay, any question? Okay, so I will, so you can screenshot this problem to make it faster. Yeah, you can screenshot this problem and then you can work on that. And yeah, it will due tomorrow at 7 o'clock in the morning. Yeah. Okay. So that will be the end of today's class. Thank you. And I'll close this class. Wassalamualaikum warahmatullahi wabarakatuh.